Hi, this is Miss Townsend. Welcome to Math with Townsend. This is a video for calculus students where we're going to look at limits of absolute value functions. So to begin with, let's talk about absolute value functions in general. This is what they look like, and we recognize the absolute value signs. Now, we know what that means mathematically. So for example, if I were to find the value of f at 6, we know that that's the absolute value of 6, which is just 6. And of course, if I sub in a negative number like -7, the absolute value of -7 is just 7. But what does that mean in terms of a function? In other words, what is the mathematical operation that we're actually performing? Well, there's not one answer to that question. When I subbed in a number like 6, what the absolute value signs did was absolutely nothing. I mean, they were just essentially ignored because the number within those brackets was already positive, so I didn't have to do anything. Whereas when I subbed in the -7 value, then the absolute value function actually made me do something to that input number. They weren't just ignored. I actually had to say, well, the absolute value of -7 is a different number. It's 7. So what is the mathematical operation that I just did? Well, what I would say is I took -7 and I made it +7. So what I did was I took my input value, in this case -7, and the operation I did was I multiplied it by a negative number. So negative times a negative is a positive. I'm changing the polarity. So the actual math I had to do was multiply by a negative or -1 to get the answer of 7. Now, what's unique and important about absolute value functions, why I have this whole separate video on them, is that I didn't do the same thing for my input of 6, right? If I had taken negative input, I would have had an answer of -6. So in some cases, my input means, well, ignore the brackets. They're not going to do anything. They're not going to change what I'm doing. And in some cases, these absolute value brackets make me change the polarity, in other words, multiply by -1. So that makes absolute value functions quite different from other functions. So think about all of these functions. I've got a whole variety of different types of functions. And for each of these, for every other type of function, when I sub in a value for x, when I put an input into the function, the math I have to do, no matter what the input looks like, is the same math. There may be cases where the number I put in might not satisfy the domain, but it doesn't change the math I have to do, right? I'm either not able to do the math at all because I have a domain problem, or I just simply, for example, in our friend the polynomial, I take the input, put it to exponent 4, multiply by 3, take the input, multiply by 8, and then subtract that from the original evaluation. So in an absolute value function, I'm doing different things depending on what my input is. That's why it's special, because it's kind of, there's more than one rule for what I do to the input. So let's examine further about that rule. So we know that the absolute value of 0 is 0. And all of the numbers sort of that are positive numbers, so when x is greater than 0, we have all of these numbers where the absolute value signs are ignored. So when I sub in any of these values, I just get the value back. It doesn't do anything. Whereas the set of numbers that are negative, so these numbers, when x is less than 0, when I sub one of those into the function, I have to do something to it because the absolute value, I have to change the input by multiplying by -1. So that's how an input of -7 would become 7, is multiplied by -1. But so there's one rule for subbing in a positive number and one rule for subbing in a negative number. And of course, for 0, we could take either of these rules and say, well, -0 is still 0. But I mean, I wouldn't even want to bother introducing -0 when you don't have to. So I would just say that, in fact, this rule is going to apply for anything greater than or equal to 0. So if I sub in 0, I get 0. If I sub in 6, I get 6. If I sub in 10, I get 10. Whereas here, if I sub in -2, I would get -2, which is 2. So that means that we can really rewrite this function as a piecewise function, because there are two different function rules depending on what part of the domain part of the real number line I'm inputting. So for some of the numbers I'm inputting, the numbers that were positive or equal to 0, I am simply just essentially ignoring the absolute value signs. Whatever my input is my output. But for numbers that are initially negative, I need to make them positive, and making a negative number positive, we do that by multiplying by -1. So we take an absolute value function and we rewrite it as a piecewise function. Then it is a single function, and we're now separating the different rules that apply into the different domains where they apply, the different parts of the domain. So in fact, absolute value functions are really piecewise functions. There are different rules. And so instead of one function rule that applies for other functions, there's more than one rule. So we break them into piecewise functions. So let's put that into practice by doing a limits question. So here's the question we're going to do. F at x equals the absolute value of x minus 2. And we're going to find the limit as x approaches 2 of the function. So how do you find the limit of an absolute value function? Well, hang on. There we go. You rewrite the function as a piecewise function, and then you evaluate the limit using standard piecewise function limit ideas. So let's examine this function so we can rewrite it as a piecewise function. So the first thing we need to know is what parts of the real number line follow one rule, which is let's just ignore it. So in other words, for some of the values of x, this function is just going to be, don't bother with the absolute value signs. They're going to do nothing. And then for some of this function, we're going to follow the rule where you do have to do something. What you have to do is calculate x minus 2, the part that's in the absolute value brackets, and then whatever you get there, change the polarity of it. And again, that's what that negative sign does. So what values work for this rule, just take the answer, and what values work for, the answer is negative, so change that polarity. Well, what we do is we just figure out what value of x would be 0, because the absolute value of 0, we know it's 0, but anything above that would be the absolute value of a positive number, and we would ignore it. So at x equals 2, right? When I sub x equals 2 in here, I get 0. So we know that x equals 2 right here is where the function rule separates. So any numbers above that, so values like 4, 7, 132, if I subbed 4 into this function, 4 minus 2 is 2, and the absolute value of 2 is just 2. I can just take exactly what I calculate. So for values that are greater than or equal to 2, and again, I want to include 0 in this set, we're going to follow the rule that says just do whatever the inside part of that bracket is, and don't change it. You're perfectly fine to just calculate x minus 2, which means for the rest of the number line, numbers that are less than 2, we need to follow the rule that says, sure, calculate x minus 2, but whatever you get, multiply by -1, because if you multiply by negative, you'll change the polarity, which is what we want to do. So that gives us both the different function rules. So again, one rule is just ignore the bracket, ignore the absolute value bracket signs. And the other rule is do the calculation, but change the polarity of your answer. And it also gives us the different domains. And from that, we can write the piecewise function. So this function as a piecewise function, so there's one set of rules when x is less than 2. There's another set of rules when x is greater than or equal to 2. So when x is greater than or equal to 2, we just do exactly what that says, but ignore the absolute value signs. The other rule is take what you have, which is x minus 2, calculate it, but then apply the negative sign. So in general, that's fine. I'm going to write it over here for a second. But you do tend to want sort of more simplified versions of your function. So I'm just going to rewrite this as -x plus 2. So I'm going to distribute that negative sign. So it's just more common to see that, a more simplified, mathematically simpler version of it. So this rule applies when x is less than 2. So I've now rewritten my function as a piecewise function. So here it is, the original question, and then the piecewise version. So I want to find the limit as x approaches 2. So, as one would expect, I'm asking you for the interesting limit, because when x equals 2, that's when I have the different function rules apply. So in a piecewise function, when you're looking for the limit where the function rule differs, that's when you want to find left-hand and right-hand limits. So first let's find the left-hand limit of the function. So I'm looking for the function rule that applies when x is less than 2, which would be this rule. And that would give me, so what I'm looking at is a nice polynomial function. So I know that as x approaches 2 from the left, it'll approach the value of 2. So if I sub -2 into that function, if I sub 2 into that function, I would have -2 plus 2, I would have 0. And then the right-hand limit. So again, the right-hand limit means I'm now following this rule. And again, that is a polynomial. So a value like 2.0001 is going to approach whatever happens at 2, which would also be 0. So my left-hand rule and my right-hand rule both agree. So therefore, the limit as x approaches 2 exists, and it is equal to 0. Let's try another one, maybe a little faster this time. So this time I want the limit as x approaches -3 and the limit as x approaches 1 of the absolute value function x plus 3. So the first thing I do is I'm going to figure out that x equals -3 is the value where this function produces x equals 0, or output 0, my bad. And that means that there are values when x is greater than or equal to -3 is going to be one function rule, and x less than -3 is the other function rule. So I can already start to write my piecewise function. There's going to be one rule, the straightforward, just ignore the absolute value signs when x is greater than or equal to -3. And there's another rule when x is less than -3, and that rule is the negative version of what I have. So I could write it like that, or I could also write it like this. And I think on the next screen I write it like this, but I mean, in this case, it really isn't a big deal which way you write it. So that is this function as a piecewise function, which means we can now evaluate limits. So there's my piecewise function. So let's first of all evaluate the limit as x approaches -3. And of course, -3 is that interesting one where the function rule changes. So we need to look at both the left-hand rule and the right-hand rule, because there's a different rule. So on the left, I'm following this rule, which is a nice polynomial linear function. So when x approaches -3, it'll act as if it's -3. So I would have -3 minus 3, that's 0. And on the right, again, I have a straightforward linear function, polynomial, so -3 plus 3, that would approach 0. And again, the left and the right both agree, which means that therefore the limit as x approaches -3 of the function exists, and it's equal to 0. Okay, so, I mean, probably saw that same answer existed. And I'll just sort of pause for a second, just give myself a new slide here. So if you remember at all what an absolute value function looks like, if all I'm doing in those functions, hold on, let me grab my pen. So if I have, pretend that's my xy axis, this is what the graph of approximately y equals absolute value of x looks like. So in all of the, and you can see what I have here is one function rule, which is the straight line y equals -x, and the other function rule is the straight line y equals x. And in both of the questions we just looked at, all I've done is transformed it by moving it left or right. So I would still have this left side meeting the right side at what you might call the vertex of the absolute value function. And so that's why we got 0 both times. Again, this is why it is nice to have studied functions visually so that when you approach them algebraically, there's more context and understanding. But let's look at a different question, something where that doesn't happen. So this time we're going to look at this function. So it is the function f at x equals -2 times the absolute value of x plus 1 divided by x plus 1. And we have 3 different limits to look at. But first, let's break this into its a piecewise form. So again, I can tell by looking at the absolute value sign. What's in the absolute value is x plus 1. So therefore, x equals -1 is where this function is going to change rules. So I can start setting up my absolute value table. We're going to have one rule when x is greater than or equal to -1, and another rule when x is less than -1. So then what is the rule? Well, if we look at sort of what the fundamental rule is, for this domain, the absolute value function is just like a bracket. It doesn't change anything. It doesn't do anything. So I can rewrite it like this. So instead of the absolute value of 1, the absolute value of x plus 1, I really just have x plus 1. That allows me to cancel this bracket. And really, it would just be equal to, no matter what I sub in, it would be equal to -2. So, and you can test that, of course. You can say, well, I'm going to sub 0 in for x. So 0 plus 1 is 1. The absolute value of 1 is 1. 1 times -2 is -2. And 0 plus 1 is 1. So this would be -2 over 0. So for any number I sub in within this part of the domain, my output's just -2. And a similar thing happens if we look at the sort of algebraic part of absolute value. So this time I'm going to take the absolute value function, but I'm thinking about the domain where the absolute value actually changes something. So it would be calculate x plus 1, but then change the polarity. So again, that's what that negative sign tells me to do. So what I have here is -2, which is 2. And then this bracket would cancel that bracket. So I would have an output of 2. And again, you can test that. Sub in -10. -10 plus 1 is -9. But then the absolute value of that is 9. So this would be 9 times -2 would be -18. And then here, if I sub -10 in, I would have -9. And -18 over -9 is 2. So that's the rule when x is less than -1. And now that we've broken into piecewise functions, let's look at these. So the first limit I want to find is the limit as x approaches -3. Now that's not the interesting value for this function. That's just a number that fits within this domain, right? -3 is less than -1. So all I have to do is look at what the function's doing. Well, the function is a constant function. So I don't have to worry about any limit issues. The left side will always meet the right side for any value within this part of the domain. So the limit as x approaches -3 is just 2. Nice. Now I'm asking for the limit as x approaches -1, and of course that's the interesting one. So the left-hand limit, we need to find both sides. The left-hand limit as x approaches -1 from the left. So from the left, I'm following this rule, and the output's always 2. And then from the right, I'm following the other rule. So now I'm following this rule. So the output's -2. Obviously, those don't match. Nope. Nope. Which means that the limit as x approaches -1 of the function does not exist. And I also asked you to find the limit as x approaches 2. So when x approaches 2, again, that's not the interesting one. That's one of the regular numbers that's mathematically boring. Still a good number. But when x equals 2, I just need to follow this rule because 2 is definitely greater than -1. And the rule says that it's a constant function, meaning it's continuous. The limits will always exist. And the limit is -2. I hope that was helpful. Please make sure that you practice math. Don't just watch someone else do math. and good luck with your studies. Bye.